and welcome to A-Level Mechanics, Year 1, Chapter 3, Forces of Motion. This is basically the biggest chapter in there, and it covers a lot of key areas that I like to sort of throw at you in exams. Before you start off with the main work, you need to do a quick overview of vectors. Vectors basically describe any movement or any motion in two dimensions. So if you want to go from here to here, you can define it as a vector, which is basically a horizontal component and a vertical component. So we could say it's 3 squares long and 4 squares up. Any squares are long, we use the letter I for it, which is sometimes written in bold or underlined. Any squares up, we use J, which again is sometimes in bold or underlined. So overall, this vector you could write as 3i plus 4j. A few key things. Difference between a scalar and a vector. So any normal number is a scalar, and any vector also has a direction with it. So a scalar would be 7, but a vector would be 7i, because that means 7 squares to the right in the I direction. In mechanics, we have some definitions that mean the same thing, except one's a vector and one's a scalar. So, for example, displacement versus distance. Distance is a scalar, and displacement is a vector. So, for example, if you travel 10 meters forwards and 10 meters back, your displacement is 0. You haven't moved at all. However, the distance travelled has been 20 squares. And the same thing with speed and velocity. Speed is a scalar, and velocity is a vector. So the main skill we're doing with vectors is basically working out their speed and angle direction from this kind of vector here. So we've got a velocity vector. Again, velocity is always a vector. And if I quickly draw this, this is going 8 squares across and 15 squares up. So it's going to be 8i and 15j. We want the speed of this. So the speed is just going to be an actual number. The speed is going to be basically the hypotenuse of this triangle. So if you combine 8i and 15j, you get an overall speed. That's what we're looking to find out. Because this is a right angle triangle, we can just use Pythagoras. So if we call this speed x, we know that 8 squared plus 15 squared is going to be x squared. Then do some maths, and you're going to get the fact that x is going to be 15. Next, we want to find the angle of direction from the horizontal. In order to do that, we're going to use a bit of basic trigonometry. So the angle from the horizontal, this is my horizontal here, I want this angle here. That's what I'm trying to work out. And this we can just use basic trig, so we'll just quickly redraw that. We've got 8, 15, and my missing angle here. So we have opposite and adjacent, that means we're going to use tan. If you're not sure, we got your basic trig. So the angle would be tan to the minus 1 of opposite over adjacent, so 15 over 8. And again, just type it in, and that'll work it out all for you. These are the main two skills we tend to do when we have vectors in a question. Okay, so make sure you find both of those, just using GCSE, Pythag, and trigonometry. Okay, on to the actual forces and acceleration. So if we've got some sort of force being pulled by a string, there's a few forces going on it. First, we have the actual force of us pulling the string. This is going to be what we call tension. The tension in the string pulls the block along. We'll also typically have gravity. So there'll be some force of gravity. If this has a mass of m, we're going to have a force of mg of gravity pulling it into the table. However, it's not going through the table, and that's because basically the table pushes it up. We call that a resistance force, which is given the letter R. Other forces you might have, quite often you have some sort of frictional force. Okay, and all those together are going to make you just decide whether or not the whole thing moves. Again, the key formula you've probably seen at some point is F equals ma. Force is mass times acceleration, and that will basically determine whether a block is going to move or accelerate, or stay still or decelerate. Let's see that in motion. So key term, we have a resultant force. That's basically the net force acting on something. So for this setup here, I've got 20 here and 10 here. So I've got a net force of 10 newtons to the right, and by the same logic, I've got 5 newtons going to the up. So the resultant force in vector form is 10 squares to the right, so 10i, and 5 squares up, so 5j. If you want the magnitude of the resultant force, whenever you see the word magnitude, that means you want to use Pythagoras, just get a number. Okay, we don't want it in a vector, we want it as a number. So we've got 10 squares across, 5 squares up. We want to find this on magnitude, so you'd have that x squared is 10 squared plus 5 squared. Again, work that out, that's not a problem at all. Next key term, we have in equilibrium. If something is in equilibrium, that means there is no net force. There's no forces overall acting on it, so therefore it is not accelerating. So here we have a block in equilibrium. We're going to work out the missing forces. This is quite easy. If I have 20 units to the right, you must also have 20 units to the left. And if you have a force of 2g acting down on it, there must also be a resultant force of 2g acting up on it. This gets slightly harder if I have my block at an angle, but it's the same idea. So for this, we want to resolve all my forces either parallel to the block, either in this direction or perpendicular to it, so in this direction. To do that, I need to what's called resolve these forces. I need to get them pointing in the right direction. And to do that, again, we use trigonometry. Okay. So here, we're told tan alpha is 3/4. So you could find alpha just by doing inverse tan of 3/4, and that'll be absolutely fine. We don't need to. They basically always give you nice numbers. So if I had a right angle triangle, and I've got my angle alpha here, I know tan alpha is opposite over adjacent. So I have 3 and 4 here, and using Pythagoras, that means the hypotenuse is 5. So now I've got all these lengths, I can actually just work out straight from these what sine and cos alpha would be. So sine alpha is opposite of hypotenuse, that's 3/5, and cos alpha is adjacent of hypotenuse, therefore 4/5. And we're going to use these 3 things in this question now. So first, I've got this 20 newtons here, and again, I need to resolve it. And the way we do this is we're going to draw a triangle. I'm going to pen a bit thinner. So when you draw your triangle, you want to make sure A, that it's right angled, and B, your original force, the original 20 newtons, must always be the hypotenuse, must always be the longest length. And now we're going to work it out. By playing with angles, you can work out that this angle here is also alpha. So if this is 20 newtons, that means this length here is going to be 20 cos alpha. And this length here will be 20 sine alpha. If we go back to what we worked out earlier, we know sine alpha is 3/5 and cos alpha is 4/5. So therefore 20 cos alpha must be 16 and 20 sine alpha must be 12. And we can do the exact same thing here. With this force of 15 newtons. So again, we're going to draw a triangle, make sure it's right angled, and make sure the 15 newtons is hypotenuse. If this is alpha, then so will this. Which means this is 15 cos alpha, and this one here is going to be 15 sine alpha. Again, cos alpha is 4/5, so 15 times 4/5 is going to be 12, and 15 times 3/5 is going to be 9. So we've made a bit of a mess, but we can get a decent handle of what's going on now. So let's add all these forces I've done in blue back to the main image. I'm going to change colour to red for this. So let's go through all the forces. This one first, this 9 newtons. Because this 15 newtons was pulling across, we're basically pulling in this direction and in this direction. So I had 9 newtons going up. And also I had 12 newtons going across. I can do the same with these forces here. I've basically got one going down into the ground, into the slope, and one going across. So the one going down to the slope was 16 newtons, and the one going across was 12 newtons. So now all my forces are basically in this little sketch, this little bit of the picture here. If I look at my total forces going down the plane, I've got 24 newtons going down. Therefore, because we're told it's in equilibrium, all the forces must balance. So the force pulling up, or the frictional force, is going to be 24 newtons. Here I've got 16 newtons going down, and I've got X and 9 newtons going up, which means this X must be 7 newtons, so that overall these forces balance together. Okay, fairly common question, but I'm afraid it does get a bit harder than that. Okay, let's look at an actual proper force acceleration question. So we've got a block of weight 20 kilograms is being pulled by a constant force of 50 newtons. And we've got this frictional force. I should also say this was a constant horizontal force. So let's do a quick sketch. We have some sort of surface. We've got this block weighing 20 kilograms. We have 50 newtons pulling it. And we have a frictional force of 35 newtons. Because there is 20 kilograms, that will give us a force of 20g pushing down. Its force is mass times gravity. And we'll also have a equal and opposite resistive force. We don't need this question, but we'll work including just to know how it works. Part A, work out the acceleration of the block. So the only acceleration is going to be to the right hand side. So we've got F equals ma. When you're asked to work out acceleration, that's pretty much always the force you want to work, always the force you want to use, unless you've got a SUVAT based question. So the force, we have 50 minus 35, so 50 pulling it, 35 slowing it down, and that's going to be mass times acceleration. Simplifying that down, we can work out that acceleration is going to be 3/4, or 0.75. Okay, that's part A done. Part B, assuming the block starts from rest, work out the time it will take to travel 35 meters. So we're going to travel some sort of distance now. For any of this type of question, we're going to use SUVAT. And we're going to fill in what we know. So S I do know, I want it to travel 35 meters. U we also know, we're told it starts from rest, so therefore my initial velocity, which is U, must be 0. V we don't know, and acceleration we also know is 0.75. We want to work out the time, so time is what we're after. We'll then look at our SUVAT equations. To decide which one we're going to use. Say we're doing that, the formula we're going to use is going to be S equals UT plus a half AT squared. So filling that in, we've got 0 times time, S is 35, plus a half times 0.75 times T squared. So we've now got 35 is a half times 0.75, which is 0.375 times T squared. We can then work out what T squared is by dividing. Let's go to our calculator for that. So we want to do basically the square root actually, don't we? So the square root of 35 divided by 0.375. And we want that as a decimal, which gives us T as 9.66. And again, for basically all the questions in mechanics, you always refer a decimal to anything else. So therefore it took 9.66 seconds for the block to travel 35 meters. Okay, well, let's look at another type of question. So all these do with forces and acceleration. This question, we have a very common setup where we're sort of shooting some sort of projectile and angled at horizontal. So we're told a cannonball is shot at a speed of 20 meters per second. As shown in the image below, we want to work out the horizontal and vertical component of the force. So this is using vectors again. So if I just draw this as a quick triangle, we're told the initial speed is 20 meters per second. And even though these aren't distances, these are speeds instead, the same triangle still works because these are the same laws of Pythagoras and trigonometry. We need to work out the horizontal and vertical components. So use basic trigonometry. This will be 20 times cos 40, and this will be 20 times sine 40. And we can just both work this out really quickly, and that will give us the horizontal and vertical components of that force. Okay, and also typically when you want probably 3 limit figures should typically be enough. Okay, this will be more like the exam question you're going to see. We've got a cannonball is shot at a speed of 20 per second at the angle 40 degrees horizontal, just as we've just seen. We want to work out these 3 following things. So first, let's copy this across, because that will give us our breakdown of our forces. So in all these questions, you basically want to treat the horizontal side of things and the vertical side of things as 2 separate parts. So part A, work out the time taken to reach its highest point. All we care about there is height, so all we care about is going to be the vertical components of our force. And as given the formulas, it's a fair good guess that we're going to use the Suvat equations. So S we don't know, U we do know the initial speed. I'm going to say that was 12.86, just be as accurate as I can. At the highest point, we always know the final velocity must be 0, so that's when it stops going up and starts going down. Acceleration is due to gravity, and gravity is slowing it down, so we want acceleration to be negative, and time we are trying to work out. So these are our four letters we want to work out, which means we're using this equation, v squared equals u squared plus 2as. And we're going to fill in everything we know. And all we need to do now is just solve this equation. Okay, and that's fairly basic. I'm going to take this 12.86 squared across and divide by all this stuff here. So 2 times minus 9.8, and that'll give me what t is. And we can just throw that into our calculator to give us our final answer, which in this case t is 8.44. Okay, so that was part A done. We want the time taken until it hits the ground. This is a very straightforward one. We know that for any parabola, anything being shot without air resistance, it's going to be perfectly symmetrical. So basically it'll take half its time going up and half its time going down. So we know the time going up was 8.44. The time it hits the ground will just be double 8.44, which gives us 16.88. Lastly, we want the total distance travelled once it's hit the ground again. So distance travelled is basically its horizontal distance. So because we've ignored air resistance, for the whole time it was in flight, it had this horizontal speed. So we could use a Suvat equation. You don't really need to because it's almost too simple for that. We can just use the base GCSE equation, which is speed is distance over time. However, here I want to work out the distance. So when the speed isn't changing, the distance is just going to be speed times time. Speed we're given, that is 15.32, and the time we're also given is 16.88. Times those together, and that will give us our total horizontal distance travelled. And because it's on the ground again, that's also our total distance travelled, because the total vertical distance travelled was 0 in this case. So we've got just over 250 metres travelled. Okay, moving on from this, we have a few special cases. There's basically the same type of questions that always come up using forces and acceleration. I'm going to put these in a separate video, just because it will take a fair while to go through. Hope that helped, and thanks for listening.